Hey everyone, today I'll be solving some problems from the 2024 F equals MA exam. Starting with problem number one. An archer fires an arrow from the ground so that it passes through two hoops, which are both a height h above the ground. So if we were to draw this, okay, so you have an arrow that's launched from the ground, and so it passes through two hoops. Just say they're both a height y equals h above the ground. And it passes through the first hoop 1 second after the arrow is launched, and through the second hoop another second later. And we want to find the value of h. Okay, so if we say that it's launched at t equals 0, um, then we can use the kinematics equation, y equals v0t plus 1/2 at squared. And since we have two unknowns, so we don't know the initial y velocity, and we also don't know the value of h, we need two equations to solve for both of them. So we can basically plug in this equation for time t equals 1 and time t equals 2. So for time t equals 1, it's at height h. Time t equals 1 plus 1/2. So the acceleration is constant. It's going to be gravity, so negative g. So we just chose the upward direction to be positive, which is why we use negative 10 for gravity. So it's just 1 squared. So we get h equals v0y minus 5. And then if we plug it in for t equals 2, we're going to get h equals 2v0y minus 20. So now we can equate these two equations. So v0y minus 5 equals 2v0y minus 20. And so we get that v0y is 15, which makes h equal to 10 if we plug it in back here, which is option B. So B is our answer. Okay, moving on to problem number 2. An amusement park ride consists of a circular horizontal room. Okay, so it's going to look like this. And we have walls which are angled back at 30 degrees with respect to the vertical. So the vertical, it's like 30 degrees away. And we can imagine that its walls extend outward like this. And so we have a rider leaning against the outer walls. So you can imagine someone standing here. Okay. And the rider's center of mass is 5 meters from the center of the room. When the room begins to spin about its center, at what angular velocity will the rider's feet first lift off the floor? So if we draw a free body diagram, we know that we have gravity acting downward. We have a perpendicular normal force from the walls, and we also know it's frictionless. There's no friction from the walls, but there's going to be friction. There's going to be normal force. You can say this is N1 and N2. And we also have friction from the floor of the circular room. So we're asked to find what the angular velocity is when the rider's feet first lift off the floor. So when the rider's feet first lift off the floor, we know that the normal force must be 0. So this is basically gone. And so is friction. So now we know that the only two forces acting on the rider are N1 and mg. So we know that N1 sine 30 degrees, so the vertical component must be equal to mg. And we know that N1 cosine 30 degrees, which is pointing inward, must be providing the centripetal force required to keep the rider in motion. Okay, so we know that sine 30 degrees is just 1/2. So N1 equals 2mg. And we also know that if we plug in this equation, 2mg, so cosine 30 degrees, root 3 over 2, equals m w squared, which we're trying to find, and r. So r is just the distance of the rider's center of mass from the center, which was given to be 5. So once we plug these in, so we get that w equals a square root of g root 3 over 5, which is a square root of 2 root 3, which is roughly 1.9. So our answer is A. Okay, moving on to question number 3. So we have a bridge that's made of 5 thin rods, rigidly connected at 4 vertices. We're given that the ground is frictionless, so it can only exert vertical normal forces at B and D. The weight of the bridge is negligible, but person stands at its middle, exerting a downward force F at vertex C. And we want to know which rods are going to be in tension. Okay, so for something to be in tension, we know that it must be like stretched or extended. So essentially what it's asking is just what rods are going to be extended or stretched if we have a force here, a force F exerted at that point. So if we draw the diagram, we have this force here. Okay, so we know that if you pull downward here, intuitively, these two rods are going to be stretched, right? Because they're going to go from, this to this. And the vertical rod is also going to be stretched, right? Because we're pulling down on it directly. But the diagonal rods are going to be unaffected by this force here. They're just going to remain in the same position. It's just these rods that are going to be stretched. So our answer should be that these two rods and the vertical rod are stretched, which would be D. Okay, moving on to problem number 4. So for our next problem, we want to graph the kinetic energy of a bouncy ball that's thrown vertically upward from the ground, knowing that the collisions with the ground are perfectly elastic. So if we graph this, so we know that K, kinetic energy, is just 1/2 mv squared. And so if we want to know like what the derivative or like the instantaneous slope of the graph will look like at various points, we can take the derivative of this, and by the chain rule we get it's just this, which is m times, so v times a, just dv over dt. So we know that at various points, the derivative of this function is just mva. Okay, so at the instant that the ball is thrown upward from the ground, we know that it's going to be at its maximum velocity, and that as it rises over time, its velocity is going to decrease. And we also know that the acceleration is always constant, and so is the mass of the ball. So the only thing that changes the derivative over time is the velocity. So as we decrease the velocity, the derivative is going to decrease. So if we start with a maximum velocity, and it's going to be starting at its maximum kinetic energy, that means the derivative is going to be the greatest when we start. So it's going to look something like this. And it's going to decrease over time. And once the kinetic energy is zero, which means v is zero, that means our derivative is also zero. So we're going to have like a flat point here. And then after that, so this portion of the graph models what the ball will do after it starts falling again. So its derivative is slowly going to increase over time, right? Because we have v is increasing. It's going to be like this. So now what's going to happen when it collides with the ground again? So if we start from here, so let's just say that, it's at this point right now, and it's about to collide with the ground. So what happens after it collides with the ground? All that happens is that the direction of its velocity changes because it's completely elastic, which means that its speed doesn't change, but its velocity does. Which means that its kinetic energy shouldn't change, right? For example, if we have 3 meters per second, it's falling at 3 meters per second here, and it changes to negative 3 meters per second. V squared is still going to be the same. So kinetic energy, the magnitude, remains unchanged. But the derivative should change sign. So now it's just like a reflection. The derivative changes sign, and it continues like this. And so the graph that most matches this is D. So that's our answer. Okay, moving on to number 5. A massless inclined plane with angle 30 degrees to the horizontal is fixed to a scale. A block of mass m is released from the top of the plane, which is frictionless. And so we want to know what the reading on the scale is as the block slides down the plane. So have the block okay, and we have a scale. I never asked for the reading on a scale. It's just the normal force that the scale is exerting upward. So one big hint that we have here is that the inclined plane is massless. So whenever you have something that's massless, the net force has to be zero. Because if F equals ma and m is zero, the net force always has to be zero. So what are the forces acting on the plane? So it has to exert a normal force on the mass, which means that by Newton's third law, it's also going to experience this force here. And it's also experiencing a force from the plane. So we have these two forces, and we want these forces to be balanced. So we know that if we break this up into its components, the horizontal component of the force is going to be balanced by some friction between the inclined plane and the scale. But the vertical component is going to be completely balanced by this normal force we're talking about. So all we want to find is the vertical component of this normal force. So we know that the vertical component of the normal force is just mg cosine theta. And so if we draw this here, so this is going to be 90 degrees. So this is 60 degrees, which means this is 30 degrees, and this is 60. So this is 30. So the vertical component is going to be n cosine 30 degrees. So n cosine 30 degrees is just mg cosine squared of 30 degrees, which is mg times root 3 over 2 whole squared. So we get 3mg over 4, which is C. Okay, number 6. A pendulum is made with a string and a bucket full of water. When the string is vertical, the bottom of the bucket is near the ground. Okay, then the pendulum is set swinging with a small amplitude, and a very small hole is opened, which allows water to leak at a constant rate. So you want to find a graph that best shows the amount of water that has landed on the ground as a function of position. Okay, so we know that if you have like a pendulum with a very small amplitude, so you like pull it with a very small amplitude, you can basically approximate the velocity at its very small, angular displacement as v, a uniform v throughout. Um, which means that for this, since the bucket has a very small amplitude, it's essentially moving at the same velocity across its oscillation. Which means that if we were to model how much water leaks during this time, it would be approximately flat. But at the ends, its velocity is zero because it's stationary. So those are where the peaks are going to be. Um, so our answer has to be C. Because as we can see, it's basically flat here, um, and the peaks are at the ends. Okay, moving on to question number 7. So we have a particle, it's traveling in a straight line, and we have its velocity as a function of time. And we want to find its velocity as a function of distance x from its initial position. So whenever we're working with these problems, we always want to think about derivatives, just like we did for problem number 4. Okay, so how can we relate the derivative of velocity with respect to x with the derivative of velocity with respect to time? So we know that what we want to find is this. We want to find this, and we're given this. So we can just multiply it with dt over dx, which is essentially just 1 over v. So if we're relating these two derivatives, this is all we're looking for in our new graph. So, okay, if we look at this portion of the graph, so the linear increasing portion of the graph, dv over dt is constant, right? Because it's linear, its derivative is constant here. But v is changing, v is increasing, which means that in our portion of the graph, when we're looking at v and x, we want the derivative to be decreasing. So we want it to look something like this. It's really large and it slowly decreases. Okay? Now dv over dt is 0, and v is constant. So since this is 0, we know that dv over dx is also 0. So the derivative is also 0 here. And then at this end, we know that, again, dv over dt is constant, but v is decreasing, which means that over time, we basically want the derivative to start at a lower value and then increase over time. So that means our answer should be C. Okay. Okay, next problem. We have this rod of length L. So we have a rod here. And we know that this point is moving at speed v. And we know that the angle with the horizontal is 45 degrees. And we know this is length L. And we are asked to find what the speed of the middle of the rod is. So what is the speed of this? So it's actually a really interesting problem. So the intuition behind it is that the rod, all points along the rod have to have the same velocity. If you think about it, if you have a rod, right, its length doesn't change, which means that either the rod is like stationary, so all points have zero velocity, or it's like moving, where all the points have the same velocity along the line of the rod. So that's the intuition we can use to solve this problem. So if we look at this, so we can basically split this velocity to two components. Right? We can have one along the rod and then one here. So we know that since this is 45 degrees, so is this, which means that the velocity of this point along the rod is v over root 2, and the velocity here is also v over root 2. So what that means is that for this point, and also for the middle, both of them have to have a velocity of v over root 2 in this direction. Now, as for the case of this point, we know that the direction of its velocity, since it's moving directly down, is here. And since this is v over root 2, and it's making an angle of 45 degrees, we know that there has to be another component here with v over root 2, which means that the velocity of this point, which is moving directly down, is also v. So now, by symmetry, we have a point moving down with velocity v, and a point moving to the right with velocity v. Which means that for the middle of the rod, if we redraw this diagram, uh, okay, it's going to have two components, right? It's velocity. It's going to have a rightward component, and it's going to have a downward component. Now, since we know that for the rod, the downward and rightward components are equal, by symmetry, we know that these two also have to be equal. We'll just say they're v prime. Now, if these two are equal, we know that the overall velocity of this point has to be in this direction. And we already know the velocity in this direction, which is v over root 2. So v over root 2 is our answer. Okay. Next problem, number 9. When a car's brakes are fully engaged, it takes 100 meters to stop on a dry road, which has coefficient of kinetic friction mu k equals 0.8 with the tires. So now if only the first 50 meters of the road is dry and the rest is covered with ice with coefficient of kinetic friction 0.2, what total distance does the car need to stop? Okay, so if a car's brakes are fully engaged, we know that it takes 100 meters to stop on a dry road, which means that if a car is moving, and the brakes are engaged, for mu k equals 0.8, it takes 100 meters to stop. And for this problem, we're assuming that the car is initially moving at some velocity v. And so we know that now we're asking for the first 50 meters of the road to be dry and the rest being covered with ice. So if we know that the first 50 meters have mu k equals 0.8, just like this one, but now we have a stretch of ice with mu k equals 0.2. So basically what it's asking us to find is, okay, we have all this like initial kinetic energy and we have friction that's basically doing work on it for this distance, right? So we know that 1/2 mu mv squared equals mu k mg times x, where x is 100 meters. So now for this, we know that 1/2 mv squared, which is mu k mgx, where x is 100, equals mu k mg times 50 plus, now how much work is required to stop the rest of the energy with a new mu k2. Okay, that's all we're asked to find. So, okay, if we plug these in now, we can cancel out m, we can cancel out g. So we know that this is 0.8 times 100 equals 0.8 times 50 plus 0.2 times x, which means that 0.8 times 50 equals 0.2x, and so x is 200 meters. So x is 200 meters, which means that essentially you need 200 meters more if you start with 50 meters over here. So the problem is asking for what total distance the car needs to stop, which is going to be 250 meters. So moving on to question number 10. So you have a block of mass m that's connected to the walls of a frictionless box by two massless springs. And the whole system is rotating, so around this, with constant angular velocity w. And suppose the block stays at a constant distance r from the axis of rotation without touching either of the walls. What is the value of r? So the way to do this problem is you realize that the springs must be providing the necessary centripetal force in order for the block to basically rotate about this axis at a constant distance r. So we know that since the initial length of this spring is L, it must be stretched by r minus L. And since this is stretched by r minus L, this must be compressed by r minus L. So, and since the spring constant of the first one is k, and the second one is 2k, then the force provided by both of them would be this. And so this force would be equal to the necessary centripetal force for this block to rotate, which would be mw squared times r. And so now we're asked to find the value of r. So we can isolate it. So 3kr minus 3kl equals mw squared r. And so r times 3k minus mw squared equals 3kl. And so r is equal to 3kl over 3k minus mw squared, which gives us d. Okay, so for problem number 11, so you have two hemispherical shells that are pressed together to form an airtight sphere. So you press it together at a high altitude where the air pressure is half the value at sea level, and then it's returned to sea level. You want to figure out what force F you need to apply outward to each hemisphere to pull them apart. So you know that um, so basically what you want to do is you want to figure out um, the force that's required for you to pull on each hemisphere in order to pull the two hemispheres apart. So you know that since it's closed, where P equals 10 to the fifth over 2, that means the inward pressure force. So let's consider one hemisphere. So the inward pressure force is going to be 10 to the fifth over 2 times pi r squared. So pressure times area. And then the outward pressure force is going to be 10 to the fifth times pi r squared because the air pressure at sea level is double this. And so we just want to figure out like what force we need to basically balance the forces, right? To basically pull them apart. So that means F is going to be 10 to the fifth over 2 times pi r squared, which is 10 to the fifth over 2 times pi times 0.4 squared, which gives us about 25,000 newtons, which is A. So moving on to problem number 12. So we have a space probe of mass m at point P, which traverses through a cluster of 3 asteroids. So at points A, B, and C, with masses m, 2m, and 3m. And we were asked to find what the torque on the probe is about point C. So the way to think about this is basically just the definition of torque, right? So we have this one. We have this asteroid, 3m, and this one, and we have the space probe, and we're given some important distances as well. So these are both d, and so is this, and so is this. Okay. The definition of torque is just if you have a force, right? You want to find so the force, and then you have some point. So basically, what you want to do is for the torque, you want the force F and the perpendicular distance from F to the point. So let's say this is R, and our torque is F times R. Um, so if we were to do it for this, we would find that, okay, so what are the forces acting on M? And what forces produce torques about this point? So the only two forces would be the gravitational forces from these two, because the gravitational force from this would pass through this point, so it wouldn't have any torque. So for this force, it would be G mm over, so R, which is the distance between them, is just d root 2 squared, which goes through here. Now, if we want the perpendicular distance away from this, well, we notice that, okay, this is 45 degrees, right? Because both these are D. And so this is 45 degrees, and so is this. So this is 45 degrees. This is also 45 degrees. It's the right triangle. And so this is D, which means that this is D over root 2, and this is also D over root 2. Which means that the perpendicular distance from this force is just D over root 2. So this is the torque due to this force. So you multiply it by d over root 2. And so the torque from this force, which also has the same perpendicular distance of d over root 2, we want the total torque. So we're actually not going to add them because if you think about it, the torques are acting in opposite directions. So since we want to find the magnitude of the torque, we're going to do the absolute value of the difference. So this force is 2 gmm over d root 2 whole squared times d over root 2. And if you simplify that, you would get GMM over 2d root 2, which would give you A. Okay, moving on to problem number 13. So you have two frictionless blocks of mass m that are connected by a massless string, which passes through a fixed massless pulley, which is a height h above the ground. And you want to find what shows a plot of t versus x, where x is just this distance. So the way to think about this is, so if you have this pulley, right? Okay, a pulley, and you have this mass m, and you have the other mass m, which is given to be a distance x away. So if we look at the graph, what we can do is consider different points on it, and consider points that are easy to identify. For example, the point where x is 0. So what would the tension be there? So if we consider when x is 0, well, it's just going to be, okay, you have a pulley like this with m here and m here. Since the forces acting on these are equal, it's not going to move, which means that t is simply equal to mg. So we can eliminate all graphs where t is not initially equal to mg. So it's basically not c, so it's either a, b, d, or e. And then what we can notice is that as x approaches infinity, we have different values of x for all of them. So this one is mg over 2, this one's mg, this one's 0, and this is, I guess, goes to infinity. So let's consider what happens when x is infinity. So when x is infinity, it's gonna look like this, right? It's sort of like this is horizontal, and so this is how it's gonna look. So if we consider this, what's happening is that we have a constant tension throughout. So T equals MA, and you also have that MG minus T equals MA. So if we add these two equations together, we get that MG equals 2MA. So A is G over 2, which means that T equals MG over 2. And so the only option that satisfies this is option B. So that's our answer. Okay, number 14. A bead of mass m can slide frictionlessly on a vertical circular wire hoop of radius 20 centimeters. The hoop is attached to a stand of mass m, which can slide frictionlessly on the ground. Initially, the bead is at the bottom of the hoop, the stand is at rest, and the bead has velocity 2 meters per second to the right. At some point, the bead will stop moving with respect to the hoop. At that moment, through what angle along the hoop has the bead traveled? Okay, so let's consider what happens when uh the bead stops moving, right? So you have this bead on the stand. So in what directions can the stand move? So we know that it's just moving on the ground, which means the only way it can move is here. Which means that if the bead is stationary, with respect to the stand, that means, first of all, the bead is not moving upward, right? And second of all, it's moving along with the stand in this same direction and same velocity. Which means that, let's just say the stand is moving at, I don't know, 0.5 meters per second, and so is the bead, right? So that's what it means to be stationary with respect to the stand. So if we consider conservation of momentum, and the reason we can use conservation of momentum is because there's no net forces in the horizontal direction acting on the stand and the bead. So we can conserve momentum in the horizontal direction. So initially, the bead is moving with velocity 2 meters per second to the right. And so if they're both, if the bead is no longer moving with the stand, that means it has to have the same velocity. Um, so if both of them have the same velocity, that means v is then equal to 1. Which basically means that we're considering an instant where the bead is not moving upward at all. It's just stationary and it's moving to the right at 1 meter per second along with the stand. So what we want to know is through what angle along the hoop the bead has traveled. So what we can do is we can conserve energy. So we can see that if it moves up h, all right. So this is our final energy. So this is the bead, and this is the stand, and this is the initial energy, which is 1/2 m say v initial squared. So if we plug these in, we can cancel out m. We get m g h plus 1/2 times 1 squared plus 1/2 times 1 squared. And then we get this would be 2 equals gh plus 1. So gh equals 1, which means h equals 0.1 meters. And so, okay, how does h compare to r? So r is 20 centimeters, which is 0.2 meters. So basically h is just, if this is the hoop, then if we draw this, this is theta. Then we know that h is 0.1. And we know that r is 0.2. So we know that cosine of theta is 0.1 over 0.2. So cosine theta is 1/2, which means theta is 60 degrees. So our answer is C. Okay, moving on to problem number 15. The viscous force between two plates of area A with relative speed v and separation d is F equals NAV over d, where N is viscosity. In fluid mechanics, so this number is a dimensionless number proportional to N, which characterizes the importance of viscous forces. Which of the following could be the definition of this number? Okay, so let's just say the number is O. So what we're given is that we have this number O that's proportional to N, which is viscosity. So what we can do is that we can use this formula to find the units of viscosity. So we know that F equals NAV over D, which means that N equals FD over AV. So it's just, so these are units of force times, okay, D, which is meters, over M squared times M over S, which would be, so these go away, this goes away, this goes away, and this goes away. So it's kilograms over meters times seconds. So these are units of N. Okay. And so now what it's asking for is what combination of units would essentially allow this number to have no like units because it's dimensionless. So now we need to look at, okay, so we know that rho, so its density is has these units, right? Kilograms over meters cubed, because it's just mass over volume. Surface tension, um, surface tension is, okay, so to derive surface tension, you could remember that, I guess energy equals surface tension times area. So surface tension is just energy over area, which is, okay, so it's kilograms per second squared, which basically means that surface tension is just force per unit length. And then length, well, that's just m. So now basically what we need to do is we need to see which one of these yields a dimensionless number. And so by plugging all of them in, we find that our answer is actually E. So let me show you guys why this is the case. Okay, so this is n over the square root of rho times surface tension times meters. Okay, so if you plug these in, you see that mass cancels out. This becomes meters squared, so it just becomes this over this, which goes to 1. So we see that there are no dimensions left, which is why E is our answer. Okay, problem number 16. A child of mass m holds on to the end of a massless rope of length L, which is attached to a pivot at height h above the ground. The child is released from rest when the rope is straight and horizontal. And so at some point, the child lets go of the rope and lands a distance d from the pivot. Okay, and so we're basically asked to find what the new maximum possible value of d is if we're on the moon, which has 1/6 of the gravitational acceleration. So for this problem, we can just assume without loss of generality that we let go, or the child lets go of the rope here. So like at the bottom of the trajectory, to make it easier to calculate. So if we assume that, then first of all, uh, we know that its speed is going to be this by conservation of energy. And we know that the time it takes to fall, since it's moving completely horizontally and has no initial vertical velocity, is just going to be this distance. So root, so the time it takes to fall, going to be root 2h over g, where h is this. And which means that d is just vt, which is root 2gl for g. Cancel these out. We get 2 root l times h minus l, which basically shows that it's not dependent at all on g. So even if we do on the moon, which has 1/6 of the gravitational acceleration, the new maximum possible value of d will be the exact same. Okay, problem number 17. We have a system of massless and frictionless pulleys, ropes, and springs So initially a block of mass m is attached to the end of a rope and the system is in equilibrium. Next, the block is doubled in mass and the system is allowed to come to equilibrium again. During the transition between these equilibria, how far does the end of the rope where the block is suspended move? Okay, so for this problem, we need to consider the different forces there are and like the different values of tensions that are there. So for example, for the pulley on the top, so it's K, 2K, it's connected to this pulley, which has a spring of spring constant 3K and this mass. Okay, so let's consider the system initially. So basically what's happening is that your tension is equal to mg, and so the tension is uniform throughout, which means that this spring is also stretched enough to provide that tension. So you can say that the amount it's stretched initially is equal to this, g, which is just t over 3k. So this is how much it's stretched initially. And then for this one, well, we're given that the pulleys are massless. And so what forces are acting on this pulley? So we have a downward tension here and a downward tension here. And we also have this supportive force, which has to be 2t, because the net force on a massless object has to always be 0, which means that this is also 2t, which means that these tensions are also t. So this spring is going to be stretched mg over k, and this spring is stretched mg over 2k. So now what it's asking is, what's going to happen if we replace it with 2mg? So what's going to happen then is that the tensions are going to change, which are going to make the springs stretch more. So for example, for this spring, instead of mg over 3k, it's going to be 2mg over 3k. So the change in the amount it's stretched is mg over 3k. For this spring over here, instead of mg over k, it's going to be 2mg over k, which means it's going to be stretched by mg over k. And then for this spring, it's going to go from mg over 2k to 2mg over 2k, which is mg over k, which means it's going to be stretched by, if we subtract these, mg over 2k. So basically what these quantities represent are how much more the springs are going to stretch now. And so if you think about it, when this spring is stretched, what happens? It stretches, which drives this one down. When this one's stretched, and this one's stretched, the same exact thing happens, right? It's gonna move, this thing's gonna move down, which is gonna push this further down. So essentially what it's asking is, if we add these, right, how much more is this mass gonna move down? So we get mg over k plus mg over 2k plus mg over 3k, which is, so we have a common denominator of 6k, we are going to get 6mg over 6k plus 3mg over 6k plus 2mg over 6k, which gives us an answer of 11mg over 6k, which is E. Okay, moving on to question number 18. So we have that a satellite is initially in a circular orbit of radius r around a planet of mass m, and that it fires its rockets to instantaneously increase its speed by delta v, keeping the direction of its velocity the same, so it enters an elliptical orbit whose maximum distance from the planet is 2r. What is the value of delta v? Okay. So basically what it's asking is you have it initially in a circular orbit and then just increases its speed so that it enters a new, like a bigger orbit, an elliptical orbit that goes like this. And you want to find what the increase in speed has to be. So, and they also give us a really big hint here that we have to use energy. So initially, when you have um, a planet, or sorry, a satellite that's orbiting another planet in a circular orbit of radius r, so its velocity can be found by basically equating forces. So if we say that this is m, so m, the force on it is going to be gmm over r squared, which is providing the entire centripetal force necessary for it to stay in orbit. Um, so this leaves us with this, which means that v is root gm over r. So that's our initial velocity. Now in an elliptical orbit, what's the new velocity going to be, right? So for that, we can use energy. We can say that, okay, so basically it went from this to now it's like this, right? Um, so now we can basically say that its new velocity at this same point, right? So basically what it's asking is that we increase the velocity here. So what we can do is we can use energy to say that, okay, when it comes back, it's going to have that same velocity. It's going to have v, which was its initial velocity, plus delta v, okay? So we can say that, okay, now its kinetic energy at this point has to be this. Now what's its potential energy? Its potential energy is this, right? And its total energy is given by this formula. So its total energy in an elliptical orbit with semi-major axis A is negative gm over 2a per unit mass, which means if we want it for this one, where we're going to say it has like, a small mass m, it's just negative gmm over 2a. So its total energy by this formula is gmm over 2a, where whenever you have the semi-major axis A for an elliptical orbit, it's just asking you for this average of these two distances. So we know that this is r, this is 2r, so the average is 3r over 2. So if we were to solve for delta v, we would get that, so this is just 2 gmm over 3r. Okay, so if we take out small m, and we multiply it by 2, we get that delta v is just square root this minus v, which is just, since we know that v again is root gm over r, it's just root 4 over 3 minus 1 times root gm over r, if we just factor out the root gm over r. And since it's asking for it in terms of root gm over r, we can plug this into our calculators. and get that it is 0.15 root gm over r, which is B. Okay. Next problem. Problem number 19. A wheel of radius r has a thin rim and 4 spokes, each of which have a uniform density. The entire rim has mass m. 3 of the spokes each have mass m, and the fourth one is 3m. And we want to figure out what the angular frequency of small oscillations is if it's suspended on an axle passing through its center. So the formula for the angular frequency of small oscillations for an object is W equals root mgh over I, where this is just the distance so the vertical distance of the center of mass from the axis about which it's being rotated. So if we were to do this for this wheel, so the mass is 7m because we have 4m plus 3m, 7m times g. So HCM, we can find that by basically finding the center of mass, the vertical location of it, and I, we can also find that. So to find the vertical location of the center of mass, we realize that these three, so this rod, and this ring, all have their vertical center of masses along this line. And so what we want to find is how much the vertical location of the center of mass deviates from this axis. So we know the center of mass of this spoke is here. Center of mass of this spoke is here. So we can find the vertical location of the center of mass by basically considering this as the origin. So this is 0. So we know that it's going to be m times, radius r, so this is r over 2 plus 3m. Now since this is the origin, this is going to be negative r over 2. Negative r over 2. And then over the total mass, which is 7m, which is going to give us mr over 2 minus 3mr over 2 over 7m, which is negative 2mr over 2 over 7m, which is just negative r over 7. Okay, so that's the location of the center of mass, and that's how far away the center of mass is from this axis. So r over 7. Okay, now for I, the moment of inertia, we're trying to find the moment of inertia of this wheel about this axis. So using the formula for the moment of inertia of a rod about this point, we know that's 1/3 mr squared. Sorry, 1/3 ml squared. So for these four, it would just be 1/3 r squared. So times 3, because there are 3 of them, plus 1/3 times 3m r squared for this one. And then for the wheel, it's just mr squared by the definition of the moment of inertia of a hoop. So if we add these up, we get 3mr squared. Okay, so plugging these in, we get, so 7m times r over 7, just mr. So mrg over 3mr squared. Square root of that is just G over 3R, which gives us A. Okay. For problem number 20, so we have that four massless rigid rods are connected into a quadrilateral by four hinges. And so the hinges have mass M and allow the rods to freely rotate. A spring of spring constant K is connected across each of the diagonals so that the springs are at their relaxed length where the rods form a square. And so if the square is slightly compressed along one of its diagonals, its shape will oscillate over time. What is the period of these oscillations? Okay, so if we're considering, just compressing it along one of its diagonals, we can basically assume that the only thing we're considering is this, which is the mass. So the mass, the spring, and the other mass. Because we're given that these are massless rods, and they don't really contribute to the oscillation. And so this is a very common kind of arrangement. And so the way we can deal with this is through this thing called a reduced mass. So whenever you have this arrangement, and you can derive this by yourself, but so if it's MA, this is MB, and this is K, then the reduced mass, so if we're writing the angular frequency of oscillation, so recall that if you have if you have the system, right, and you push it, small distance x, the angular frequency of oscillation is just root k over m. So if we're trying to use the same logic for this, and we're basically trying to convert this into an equivalent system like this with an effective mass, then the formula for the effective mass is simply MA times MB over MA plus MB. And we can basically plug in this effective mass into this equation. So if we have both of them having the same mass m, our effective mass is going to be m times m over 2m, which is m over 2. So if we plug that in to equation for W, angular frequency, just root k, so root 2k over m, which would basically mean that since we're finding the period of the oscillations, since period is just 2 pi over W, this would be 2 pi root m over 2k, which would be B. So moving on to problem number 21. So we have a syringe filled with water of density rho and negligible viscosity. Its body is a cylinder of cross-sectional area A1, which gradually tapers into a needle with cross-sectional area A2, which is much smaller than A1. So it's held in place, and its end with area A1 is pushed inward with the force F, so that the end moves with constant speed V, and water shoots straight out of the needle's tip. So the region with cross-sectional area A2, and we want to find the approximate value of F. Okay, so if we consider forces on the syringe, so it gradually tapers from A1 to A2. So we have a force F acting on this end. We also have internal pressure from the fluid inside, and we also have atmospheric pressure. that's pushing here. So we know that since this end is moving at constant speed v, it has zero acceleration, which means that the net force is zero. Okay. And what we also know is that since this end is moving at v, that means a1 times v must be equal to a2 times the rate at which water is basically shooting out of the needle's tip. We can say that's v2. So a1v equals a2v2. This is a principle of all fluids. So if you have like some like container that's holding a fluid and you have two different areas, a1 and a2, and they're moving at speeds v1 and v2, a1 v1 always equals a2 v2. So we can use this relation, and we can also use Bernoulli's principle. So Bernoulli's principle states that so pressure plus 1/2 rho v squared plus rho gh is always constant for fluid in a container. So if we apply this formula to these two areas, we see that initially it's going to be P plus 1/2 rho v squared plus rho gh. So for this region, pressure is P. There's no kinetic energy because although you're pushing this end, the water inside is not moving relative to the end. So there's no kinetic energy, and we'll say that it has some potential energy because it's at a height h. That's equal to the atmospheric pressure because the water is now outside of the container plus 1/2. So it's moving, so it has kinetic energy 1/2 rho v2 squared plus rho gh. Because it's basically at the same height, so rho gh cancels out. So we get that P minus atmospheric pressure equals 1/2 rho v2 squared. And so since we're solving for the approximate value of F in terms of these quantities, we can now notice that F is simply P minus atmospheric pressure. So now we can get a relation of F in terms of density. And we can also notice that V2, based on this relation, so the relation here of A1V being equal to A2V2, this is just 1/2 rho times A1V over A2 whole squared. So that's rho over 2 times A1 squared times V squared over A2 squared. And so actually F is equal to P minus P atmospheric pressure times A, because force is pressure times area. So it's going to be times A1 actually, because that's the region at which the pressures are acting. So this would be rho A1 cubed V squared over 2 A2 squared. So in fact, if we look here, so it'd actually be this times A1 and this times A1. And so the answer is rho V squared A1 cubed over 2A2 squared, which is D. Okay, next problem. A spherical shell is made of a thin sheet of material with a mass per area of sigma. Consider 2 points, P1 and P2, which are close to each other, but inside and outside the sphere respectively. So we basically want to find the absolute difference between the accelerations due to gravity at these 2 points. So You have a spherical shell, so it has some mass, and you have these 2 points. So a principle of gravitation is that if you have like a massed object, which is like a spherical shell, it has no at any point inside the shell is gonna have no gravitational acceleration. Because basically the forces from all these points on the sphere are gonna cancel out. So that means G1, so the gravitational acceleration here is 0. And so G2 is basically going to be like the gravitational acceleration if all the mass of this spherical shell were concentrated at the center. Um, and since it's very close to the edge of the sphere, we can basically approximate the distance as r if we take the radius of the spherical shell to be r. So now the mass of the spherical shell is going to be sigma. So since sigma is mass per area, we're going to multiply this by the surface area of the sphere. And so the gravitational acceleration is going to be g m over r squared. So g times sigma 4 pi r squared over r squared, which is 4 pi g sigma. And notice how we weren't given r, but we didn't really need it because the gravitational acceleration is not dependent on it because they basically canceled out. So our answer is D. Okay, number 23. So you have collisions between ping pong balls and paddles that are not perfectly elastic. So if a ball is dropped on a paddle from height h, it's going to bounce up to h over 2. So to keep the ball bouncing steadily, the player moves the paddle up and down so that it moves with speed 1 meter per second whenever the ball hits it. You want to know to what height the ball is bouncing. Okay, so we're given that the collisions are not perfectly elastic, and so if you drop the ball from height h, this is height h, it's gonna only go back up to height h over 2, which basically means that if the velocity of the ball here, so if it's dropped from a height h at rest, the velocity is gonna be root 2 gh. That means that its velocity when it's going back up is gonna be uh 2gh over 2, which is root gh. Which basically means that its velocity is going to decrease by a factor of root 2 after it collides. So if its initial velocity is v and its final velocity is v prime, then v prime equals v over root 2. And so this is all in the reference frame of the paddle, which means that even if the paddle is moving, we can still use the reference frame of the paddle to determine that the speed of the ping pong ball in the reference frame of the paddle is going to decrease by a factor of root 2. So we're basically given that if the paddle is moving upward at speed 1 meter per second, then in the reference frame of the paddle, sorry, in the reference frame of the ground, the ping pong ball is going to basically bounce steadily, which means that, if it collides with the ping pong, with the paddle at speed v, it's going to move back up at speed v. But in the reference frame of the paddle, initially it's moving at v plus 1, and its final velocity is v minus 1. So v plus 1 equals root 2 times v minus 1. So now we can solve for v. So we need v root 2 minus root 2. So v times root 2 minus 1 equals 1 plus root 2. So v equals root 2 plus 1 over root 2 minus 1. And then we're basically we're asked to find the height to which the ball is bouncing, which we can easily find by using the equation h equals v0 squared over 2g if it's thrown straight up. So h is going to be this whole squared over 2g. And if we use our calculators, we should get something around 1.69, which gives us d. Okay, moving on to problem number 24. So when a projectile falls through a fluid, experiences a drag force proportional to the product of its cross-sectional area, the fluid density rho f, and the square of its speed. Okay, so basically we have like the drag force. It's gonna be like k v squared, where k is the cross-sectional area times the fluid density. And so you have a sphere that's dropped in the fluid, and so when the projectile has reached half of its terminal velocity, what would its displacement be proportional to? Okay, so we can easily solve this using dimensional analysis. So basically, we know that what we're looking for is displacement, which has units meters. And we know that we have this quantity, so drag force, we have K, and we also have the ball. So we have the mass of the ball. So we can call that M, the mass of the ball. And so if we use dimensional analysis, we can see that K, so this constant, equals F D over V squared. So if we break these up into their units, this is a unit for force, and this would be the unit for 1 over V squared. So this is simply mass over length. So basically what we found here is that our constant of proportionality, which is also equal to A rho F, is equal to the mass of the ball, the mass of the sphere over um, the displacement. So now we basically want to find the L length in terms of R, rho S, and rho F. So since we can basically derive rho S from here, since we can multiply rho S by the volume to find the mass, and we also have rho F here, we can easily solve for L in terms of these quantities. So L equals mass over area times fluid density. It's going to be 4/3 pi r cubed times rho S times 4 pi r squared times rho F. So that's just going to be rho S r over 3 rho F. So displacement is going to be proportional to r times rho S over rho F, which is B. Okay. So for problem number 25, we have a yo-yo that consists of two massive uniform discs of radius r that are connected by a thin axle. So you have a string that's wrapped many times around the axle. And the end of the string is initially distance r from the axle. So basically the string is like completely wrapped around initially. So string has negligible mass, always remains vertical. And between the moment the yo-yo is released and the moment the string completely unwinds, which of the following is true regarding the yo-yo's acceleration? Okay, so to draw conclusions about the acceleration, what we can do is see how the velocity of the yo-yo changes over time. So what we can do is we can use conservation of energy to basically find how the distance that the yo-yo is dropped. So let's say it's like a distance h, how the velocity of the yo-yo changes with the distance. So we know that the yo-yo is gonna have mass m, so mgh equals, okay, so when you lose this amount of potential energy, it's gonna go into translational, so downward, and rotational kinetic energy. So it's gonna be I is gonna be 1/2 mr squared, because it's a disk, and W is gonna be V over small r squared, where small r is just the radius of like the string on the disk at a certain like time. So if we try to solve for V, we can cancel out m. 1/4 r squared times v squared over small r squared plus 1/2 v squared. Can multiply by 2 both sides. And factor out the v squared. To basically find that v squared equals 2gh times 2r squared over r squared plus 2r squared, 4gh r squared over r squared plus 2r squared. So now what we need to do to get v completely in terms of h is to see how r varies with h. So if we think about it, we know that h is simply like the amount of string that's no longer on the disk. So if we assume that the string has thickness x, then let's just say that, yeah, so let's just say the yo-yo has moved a distance h. That means the area of string that is now over here is going to be, okay, the length that remains, so L minus h, times the width of all this string, which equals the area that remains, which is pi r squared. So that means r squared in terms of these quantities is L minus h times x over pi. So if we plug it back in here, 4gh times r squared L minus h times x over pi times squared plus 2 r squared. Okay, so what we notice here is that if we plug in h equals 0, then this, which is v, v is going to be 0. And if we plug in L equals h, v is also going to be 0. Which means that when we initially drop the yo-yo, the velocity is going to be 0. And when the string completely unwinds, the velocity is also going to be 0. Which means that B through D are all wrong. Because if the acceleration is always downward, then V can't be 0, at these two times. Because this basically implies that from the time it's released to the time it stops, the net acceleration is 0, which means it can't have downward acceleration throughout. The yo-yo's acceleration also can't always be 0, because that would imply that it never moves, which is not true. So the answer has to be E, which means that there's upward and downward acceleration at different times during its motion.